we've got the equation, and this needs to be transformed into, and I'm going to write this out in full, and a and b are integers. So let's see what generates what. Well, x times x will generate the x squared. A times a will generate a constant. So, oh yes, so it'll be part of generating this 1. Now what about these two? This is going to be a times x, and this is going to be another a times x. So this on its own will generate plus 2ax. There's nothing else in this relationship that will generate the 6x. So our conclusion from that analysis is that negative 6x must equal 2ax. Well, the x's cancel. We get that a is equal to negative 6 divided by 2, which is equal to negative 3. So we've got the first of our answers. We've got the fact that a is equal to negative 3, but we don't know what b is. So let's do a little bit of side work. Let's work out what x plus a multiplied by x plus a actually generates. The first eyebrow generates x squared. The second eyebrow generates a squared. And we're happy that the two underneath ones are going to generate plus 2ax. So the right-hand side is going to be equal to x squared plus 2ax plus a squared plus b. Okay, substituting negative 3, we get x squared minus 6x, a squared, negative 3 times negative 3 is positive 9, and then plus b, that we don't know. But what we do know is that 9 plus b must equal 1. So we can write that down. So again, rearranging the furniture here, b must be equal to, subtract 9 from both sides, it appears over here as negative 9, plus 1, negative 8. So we've now found that our original equation of x squared minus 6x plus 1 can be described and is equal to x minus 3 squared minus 8. And that's the answer to the first part of the question. So with that information, let's see if we can answer part B. They're asking us, hence or otherwise, always do hence, don't do otherwise, write down the coordinates of the turning point of the graph. So just to let you visualize what's going on, I don't know where this quadratic crosses the x-axis, but the one thing I'm certain about is that given that the coefficient of the x squared term way back here is a positive 1, that it's a U-shape. And that U-shape will have a turning point, and here it is. It's the point where the graph reaches a minimum value and then starts climbing back up again. And as I've said before, that is more difficult to do from the original equation than it now will be to do it from the completed square version of the quadratic. Let me show you. Let's just have a look at this term. Being a squared term, it will mostly be positive. Because if this was a positive number inside here, if x minus 3 was positive and you square it, yes, you get the square of a positive number, which is even more positive. Equally, if this was a negative number, if x minus 3 turned out to be negative and you squared it, negative times negative is positive. So again, you get a positive answer. When is it not positive? It can certainly never be negative, but when does it have no power to be positive? Well, that happens when x minus 3 is equal to 0. And when does this happen? This happens when x is equal to 3. So when x is equal to 3, this whole term doesn't have any power to alter the curve from a negative 8 value. Any other value of x will cause this to turn a bit positive and pull the curve upwards. So the diagram, in a way, wasn't a really bad guess. This point here, the minimum point, is at positive 3. There could be other things wrong with the diagram where it crosses, but for the moment, the minimum point is sitting at 3. And what is that minimum value? Well, the minimum point of the curve, this value here, is -8. So the coordinates of the turning point is equal to, the x value is 3, and the y value is -8. And that is your answer.